Hello, I'm Stephen Foskett, and we are here in San Francisco, California for Cloud Field Day. We're at the offices of Scality, and we've invited in a group of independent writers, speakers, podcasters, and so on to learn about their technology, to interact during the presentation, and to ask questions that represent the audience outside. If you'd like to learn more about Tech Field Day, go to techfieldday.com. You can learn how to become a delegate like the folks around the table or a presenter like Scality. If you'd like to see more videos like this, just go to youtube.com/techfieldday.
I'm Giorgio Regni from Scality, and we're going to talk about durability. So the joke we made is you can buy software for the feature. If you start losing data, you're not going to keep it for long. So durability is very important. What is it? So durability is a term, I think first time I heard it was from Amazon. Actually, we use that term because I think it makes a lot of sense. It's the probability of not losing data over 1 year. So you have to think of it this way. It's a little bit like availability. So not losing data over 1 year. If you look at Amazon themselves, they're going to provide 13 nines of durability, which means you can expect an average annual loss of 0.0001% of object. So you can expect loss, right? There's no storage system where you have a durability that's guaranteed forever. But now if you turn that around in terms of number of years, that means that if you store 10,000 objects, you can expect to have a loss once every 10,000 years, or 10 million years, sorry. So that's another way to look at the same number. Right?
And it's with replication or without replication? Or
No, that's just using the standard Amazon service. So they do multiple copies in the back. You can expect to not lose an object in 10 million years if you have 10,000 objects. Right? So kind of look at it this way. The way that we designed the ring, we actually wanted to have a proof of durability. So it's not just we make enough copies. We need to be able to prove that the actual algorithms give you a certain guarantee. And so to be able to do that, we spend a lot of time evaluating what has a real impact on durability. So at the end of all our thinking, there's 4 main factors that influence durability. One is the drive themselves. So what's the physical drive mean time to failure? Which is a number that gives you the expected life of that drive in terms of number of hours. The drives have made a lot of progress. So they're not getting big as fast as we want them to be, but they made progress on durability. So you're looking at 200,000 hours, yes, for one particular drive. Now you have the speed at which you can detect failure, and that's very, very important. And so we spend a lot of time optimizing that part. I will talk about that more later on, but you need to detect failure. A lot of storage systems will not find the failure until you access the data. In that case, it may be too late, right? So the speed at which you detect a missing object or replica or parity is very important. Then you have the speed at which you can reconstruct data. So if you detect missing data immediately and you need 10 days to rebuild it, because the algorithms take a lot of bandwidth on the network, or you're limited by something else, or CPU, because of calculation, then durability is going to be very bad. So you have to rebuild as fast as possible. Then you have a geo-distribution. So if you have 2 separate systems doing a sync, obviously that's going to increase durability a lot. So you have to do a mix of the drives, detecting failures, rebuilding quickly from failure, and geo-distribution. So the way that we take these 4 patterns and implement them in the ring. So one is we have this SPROV engine. I will talk about that afterwards. You saw that the ring itself is a key space. Then the key space has projections to guarantee the location of the replicas on different machines. So all of this can be modelized in mathematical terms because it's a circle, projections. So actually did the work to do simulation based on that. And so we could assign server keys and position in the distributed system in many different ways. So we try different algorithms and to find the one that guarantees the better durability. And so when you add capacity to our system, we're actually solving a problem, which is where should I place the new servers? Should I place the new servers so that I get the maximum durability? And that means simulating a failure, looking at the durability of that. Simulating another failure and looking at the durability of that, and so on. So that's like a complex iterative process. It's a lot of math, and that gives us an MTBF for the entire platform, right?
Do you factor in aspects of the server configuration, so which drive?
Absolutely, which drive you have, the network bandwidth that you have, and the IO utilization of the platform.
Okay, so how do you get the information about the drive? So do you maintain a database of statistics on
Yes,
these
so
drives?
there's not that many drives,
Yeah.
right? Seagate, a GST,
Yeah.
and then you're going to go different capacities, but there's not that many drives to look at. So we know their durability.
Okay. So, but so that's just baked into the software?
Yeah.
Okay.
So then we build. So we build for us is a term where it's the ability for us to detect missing replicas and parities. So when you look at the projection method that we're using for replicas and parities, it's easy for us to say that I have that object. There should be another object with that key that is an exact copy, right? So each storage node is actually making these projections all the time by a group of 1,000 keys, and it's calling another store node and is asking, do you have the same keys? So do you have these 1,000 keys that you should have? And if you don't, then we're going to zoom and try a range of 500, then a range of 100, and start rebuilding whatever's missing. And this algorithm runs all the time on the ring itself. It's something that is running every day, all the time, and that's only in memory. So we wanted to make it as fast as possible. So that's checking if the keys are present. This is not checking if the drives are there. This is just checking, does that server has the object it should have? If not, I'm going to rebuild them. So that's a very, very efficient algorithm that's processed in batch command, and that's only looking at memory, doing some checksums in memory, and then doing some network operation. Then we have a disk repair, which is as soon as a drive fails, we're going to trigger a repair task. And the way that we distribute the data with SPROV, we're not going to ask for one drive to send data. Actually, are going to be at minimum 6 servers. And all the drives inside that servers are going to have the 6 servers, a little bit of the information I need. And they're all going to start sending the data in parallel. So if on a typical 6 nodes configuration, if I lose one drive, I have at least 5 times the number of drives per machine. So maybe if you have 20 drives per machine, I have 100 drives sending me a little bit of data in parallel. So we want to rebuild as fast as possible. And so the disk repair is event-driven. You lose a drive, you start repairing, and you're going to get 100 of drives participating into the repair process, right? As opposed to a RAID system where you have a group of 6 servers and you only have 3 or 4 servers helping you rebuild. In that case, I have 100 of servers helping me rebuild.
So when you expand your ring and add nodes or drives, do you restripe data to kind of rebalance across all those?
We do, yeah, absolutely.
How are you doing failure detection? Are you just doing some kind of checksumming, and then if...
Yeah, so there's a lot of IP into how we detect that, but just a rule of thumb, there's some behavior from the drives, especially in error rate, where we can detect that this drive is going to fail, and then we'll start rebuilding.
So when you detect that, do you mark that? So maybe you can only read from it, but you can't write?
So you can only read, you cannot write, and you start rebuilding right away. You don't wait for the complete failure to start rebuilding.
Do you do any kind of rewrite? I mean, bit rot of stuff sitting there, things I may not access for years. So you go back and you have
to scrub the data and detect in the background.
Do you do any kind of alerting when you detect failure?
Any kind of?
Alerting when you detect failure?
I didn't get the...
Alerting, yeah.
Oh, yeah, on the supervisor, yes, as well. And it's in MP traps when this happens. So then the other one is the multi-geo deployment, and Yannick talked about some so we can do mirror, we can do sync, we can do stretch, but each time you go multiple sites, you improve durability. So we talked a little bit about the projection mechanism. This Keyspace is between 0 and 99. So you see 5 projects to 38, that project to 71. And so the SPROV tool that is going to calculate the Keyspace actually looks at all the combinations. So from 1 replica to 12 pieces of erasure code. So it looks at all the projections, and thanks to that, it can know which is the best server placement to maximize speed of reconstruction and to minimize data loss if you lose a server. Right? It's a balance that we're always trying to optimize. So this is some of the proof of SPROV. We're not going through it, but this is the actual documents we maintain. And it's a pure mathematical proof. This is not...
It seems okay.
Yes. Can somebody check that XJ is the right one? I never do further about competitors, but a lot of competition will do, let's do 3 copies of the data and we secure. But you don't know where it goes. You cannot guarantee that it actually goes into the right place. This is mathematically proven based on the circle topology. And so at the end of the day, we get these graphs. So I'm going to show a simpler example, which is all the combination of projections and placement of servers to guarantee durability. So I have a simplest version. So this one is 6 servers. Each server has a different color. And it's up to 5 copies, so 6 replicas of the same object total. And so this is my key space, but I'm folding multiple times, right? So this is, if you go all the turns, it's 360 degrees. So that particular machine has this piece of a key space. And when it's going to project, I go to a different color that's a different machine. And so on, and so on, and so on, and so on. Each time a different machine. And then I overlap, because I don't want drives to be copied of each other. So now I'm starting with another color and projecting to a different machine, and so on. So with this, we guarantee that, what's that noise? Any projection of replica, whether I do 1 copy, 3 copies, 4, 5, 6, always fall on a different machine. And if I were to lose this yellow machine, it will work again, right? I'm not going to do that, but if I were to lose this yellow machine, you will see that each projection still continue to go on a different machine. And so that's how we compute key spaces and guarantee durability. So the way that we simulate, we're going to simulate losing a random server, then losing another random server, and continue to keep enough replicas into the system. And so if a server dies and you add 2 new machines, we're always going to compute the best placement. And it's going to be a combination of making sure that the replicas fall on different machines and making sure that in terms of server loss, if that happens, you don't have to copy too much data on the network. So just to give some statistics, so this is not a test we did, it's a test that a customer did before buying the software. So it's 6-node cluster, 6 servers, filled up to 20%. 40% usable data. They didn't want to start from a system that's empty, so there is some data in there. It's a mix of replication and erasure code, so it's not just one or the other, it's a 50-50% mix. They use 4 terabyte drives, right? And they tested the repair of a single disk and the repair of multiple disks at once. And so the performance they measured was that we could repair at 1.4 terabyte per hour. So one drive cannot do that performance, right? So if you lose a drive, you have multiple drives sending data in parallel and going to the machine that is going to load balance on all the drives in the machine. So you never have a one-to-one drive communication. That's how we can get this kind of performance. So meaning that losing one of these drives, it will take a few hours to rebuild it. In production, you may throttle that because that's going to use a lot of IOPS. So you may make it 50% of your IO capacity. So that's going to be under 10 hours. And as a rule of thumb, it has to be less than 24 hours. So you should be able to repair a drive in less than 24 hours. If you use some of the slow SMR drives that give you very good capacity, one drive cannot repair that fast. It's just too slow, if you look at the specs, to be able to repair in 24 hours. So you do need to use multiple drives and in parallel as the ingest, multiple drives in parallel as the recovery itself. And so when you use SPROV and you change the speed of rebuild, and you make it 48 hours, you're going to lose 5 nines of durability. It's very, very important to repair in less than 24 hours.
So do you have recommendations for drive types, number of drives per node, things like that, that kind of call it a reference architecture?
Yeah, it's part of our reference architecture design.
Okay.
Yeah. So this is example of configuration of our system and the durability you get. So if you get one site and you do erasure coding, ARC is the name of our erasure coding engine, and you do 9 objects plus 3 parities, that's going to give you 8 nines. 8 nines, if you were to compare to a replication system, you will need 3 copies. So the overhead here is 30%, and the overhead for replication will be 300%, because doing 3 copies. So you see why people do erasure coding. If you were to deploy on 2 sites, using erasure coding, which is 5 plus 7, so meaning the first site has 1 parity, the other side has 6 parities, as you can see here, you get 49, right? Which is a little bit more than the AWS durability for S3. So you get 49s, and the overhead is, what's the exact overhead? It's 120%.
The erasure coding only applies to large objects, and replication only applies to smaller objects?
Yes,
and change that boundary?
Yeah, so it's transparent to the actual application using our system. So if it's below 60K, we fall back to making 6 copies in that case,
right,
to match the 49 durability. So you want replication and erasure code to match in terms of durability. Otherwise, your system is not balanced. When that's a different ratio, you do 7 plus 5s over 3 sites, right? You still get a 14.9 durability, but with less overhead. So going from 2 sites to 3 sites, 5 plus 7 or 7 plus 5, gives you equivalent durability, but you have less overhead because you only need 5 parities. That's because adding a site improves durability on its own. Can you see?
I've seen those sorts of things before, where it's it's extremely rare that you'd get a failure, but there's always some little single issue there in the code that can drive that stuff bananas, right? I mean, it's not. Yeah, I understand from a hardware perspective, if everything worked properly, these things would happen very, very rarely, but it's not necessarily the case all the time.
So if you look at firmware for Drive and the number of lines of code they have, Drive is a software piece. It has so many lines of code, so it's going to have bugs.
Yeah, yeah.